All right, so this unit is about gas laws. Gas laws are kind of fun and best if you sort of experience them on your own. So, the first thing you need to understand, which I'll give you the opportunity to do, is what pressure is. Now, pressure is just a matter of gas particles colliding with some pressure monitor or basically the edges of its container. And it's best figured out. So I posted a video of atmospheric pressure, which does a pretty good job. But what I really want you all to be doing is one of these interactives. So this interactive is the University of Texas one. I've never had a problem with this until just now, but you can adjust the volume by clicking things here. You can lock the volume by doing that. You can heat it up. You can cool it down. You can put different gases in there. Pressures here. You can release the pressure here. So there's all sorts of stuff to explore, and that's the best way to do that. If for some reason that Texas one isn't working, this FET is sort of equivalent. It's a little too busy for my tastes, but the same thing can happen. Instead of a syringe, you got to do this, and you can still see what pressure results and temperature, heating and cooling like we've done. But yeah, there's a little too much going on this one, in my opinion. Anyway, all right. So you should explore all those things and get a sense of pressure. And what I do in this video is I get a balloon to get very large because I take away the atmospheric pressure so that there's nothing fighting the air inside the balloon from expanding. So watch that video. It's posted on Classroom, and that explains the same logic as to why removing air pressure helps water boil at lower temperatures. And in fact, in that video, I boil water at room temperature. So go look into all that. The temperature for this unit, remember, we talked about how it all has to do with motion of particles. And basically, we're going to need to do everything in Kelvin for this unit. So anything with gases needs to be done in Kelvin. And Kelvin is based on the notion that at 0 Kelvin, no particle is moving anymore. So there is no negative Kelvin. It's all positive. And that's the beauty of using it for this unit is you don't have to get into negatives. You want to make sure everything is a positive number. So you want to make sure your temperature stays positive. So remember to convert anything to Kelvin, you have to add 273 to the Celsius. So if I had 100 degrees Celsius, I would just add 273 and get 373 Kelvin. That's not too hard. You add 273 to degrees Celsius and you get 250. So it's always going to be positive, and that's the problem. We don't want negative numbers when we're doing these calculations for gas laws. And by adding 273 to the Celsius, we're always going to stay positive since Kelvin at 0 just means all motion is stopped. So, unlike heat, which was a big pain with a lot of its abbreviations and symbols, gas laws make sense. Pressure is a P, volume is a V, temperature is a T. So, pressure, as we just discussed, is the force exerted on a gas by a gas on the surface of something. It's all about collisions. Volume is the amount of space occupied by a gas, so that's about space. And temperature is about movement. So pressure needs to be now, unfortunately. So you know how in the metric system we've all agreed. Let's just talk about volume for a second. That volume should be in liters. So all your measurements need to be in liters when we're doing gas law stuff. And I just told you all your temperature needs to be in Kelvin so that it stays positive. Um, Pressure is a mess, and nobody can agree on a pressure unit. And so, unfortunately, pressure is can be provided in ATM, which is atmospheres, kilopascals, millimeters of mercury, which is the same as torr. Also can be presented in PSI, which is pounds per square inch. So it's kind of nutty, and you're going to have to be able to jump around among your pressure units. Thankfully, see, this is why you're going to start to wish we did adopt the metric system. Liters is only one thing. Kelvin is only one thing, but the world cannot agree how to measure pressure. So we have to follow what the world does. So you will need everything to be in liters. Occasionally, things will be provided in milliliters. That's just a matter of moving the decimal 3 places. Okay. So the decimal is here for 400 milliliters. To make it liters, we want to jump 3 places and make it zero point 0.4. 25 milliliters, the same thing. You want to jump 3 places and be 0.025 liters. So everything needs to be in liters when we're doing this. You can put things in milliliters sometimes, but if you're the kind of person who likes to embrace a rule and stick to that rule, always going to liters will never hurt you. And again, the reason we're moving everything by 3 places is because we're dividing by 1,000. Milli means 1,000. All right, there's a standard temperature and pressure. The standard temperature and pressure is called STP. The temperature at STP is 273 K. That should be easy to remember because you're already remembering what you need to add to every Celsius. So 273 made sense as a standard temperature. The pressure is either going to be 1 atmosphere or 101 kPa or 760 millimeters of mercury or 760 torr or 14.7 psi, which is pounds per square inch. So basically, it's not a problem. All of what we're about to do will work with any of these units. The key is they all have to be in the same. So you can't compare millimeters of mercury to atmospheres or kPAs to PSIs. You need everything to be in the same unit. So, for example, let's say we had a problem that had kPa, but it needed things to be in atmospheres. That means we need to convert our kPa to atmospheres. And remember, whenever anything is equal, um, so we're going to be using these two. Whenever anything's equal, we can do the domino thing. So 101.3 kPa can go down here, and the 1 atmosphere can go on top. And that'll convert kPa to atmosphere. So 123 divided by, 123 divided by 101.3 is 1.21. So that's 1.21 atmosphere. Okay, same thing here. If we got to go atmosphere to millimeters of mercury, so we're going to use this one and this one, I'm guessing, right? So we can start with the 2.5 ATM, and then for every 1 ATM, there is 760 millimeters of mercury. And so it's just 2.5 times 760, so 1900 millimeters of mercury. All right, very quickly then, Boyle's Law, what you'll experience when you do the interactive is that volume and pressure are inversely proportional. This is not surprising to anyone. Um, if you ever squeezed a bottle to knock the top off or popped a balloon, right? You squeeze the balloon in the, so you make the volume smaller and it pops because the pressure goes up. That's what Boyle figured out. And so as a graph, it would look like this situation. But if you actually uh, graph 1 over the volume versus the pressure, you'd get a straight line. So that's going to be a lab we do on Friday. Uh, so yeah, this shouldn't be surprising, right? If you have some gas in a cylinder and then you push that cylinder down, the gas is going to bounce around a lot more because there's significantly less space, so the pressure is going to go up. So the pressure goes up when you take away space, and the pressure goes down when you give it space. This is also, if you've ever been on an airplane, why your chip bag will get inflated because the air in that bag at uh, when you're on the Earth's surface, basically at sea level, is made to not be that big, but as you get in a lower pressure of an airplane, the volume gets bigger. All right. Charles' law. Charles was actually a hot air balloonist, so it makes sense that he figured this out. As you heat up air, its volume expands, right? The hotter the air, the more volume it takes. So that's why hot air balloons work. You can put a flame into a bunch of air and it'll expand and blow up a balloon. So volume and temperature are directly proportional. They go up together. If you were to graph them, they'd be a straight line like this. That's Charles' law. And then Gay-Lussac's law is that pressure and temperature are directly proportional. And if you do that interactive and you cool down the gas isn't moving as much. Because it's not moving as much, it won't collide as much, and you'll see a decrease in the pressure. So again, a straight line for this one, a straight line for that one. This one is a curvy line unless you do a little manipulation of pressure versus 1 over volume, which again we'll discuss on Friday. Those are the laws you need to know. They can actually all be combined into the combined gas law, which is to say that the pressure and the volume divided by the temperature will equal the pressure times the volume divided by the second situation. So basically, that's what's happening here. There was a pressure and a volume of this Doritos bag at atmospheric pressure on Earth. When it got into the airplane, the pressure and volume changed, the temperature even changed a little. And so, anytime you have the same situation, like or a bubble or a syringe, it has to be, or a balloon, anything that's the same amount of gas, this works. That in one situation, the bubble or the balloon or whatever will have certain characteristics, and in a second situation, it'll have different characteristics that are related because of what we just saw here. That basically all this stuff is directly or indirectly proportional.